This is an image of something called the Home Lab. It's one of the first smart homes used for research in gerontology. And we use this environment to test out various technologies of the type that Elmar mentioned. And the idea basically is to use this as a kind of a training ground to develop technologies that could eventually be rolled into the real world. So what we'd like to have in the not too distant future is for individuals like this woman to be able to live at home for longer instead of having to be moved into retirement homes or long-term care facilities, and to live at home in dignity and independence. But for that to happen, there needs to be some kind of monitoring. So there could be sensors of the type that was mentioned previously that could watch how she's moving through her environment, and microphones that can listen to her speech. One thing we've developed is robots for the home. So this is before the workshop, but the idea is that a robot can be used in the home to help people perform daily tasks and to monitor their activity. So in some earlier work, we invited 10 individuals with Alzheimer's disease into the home lab to be conducted by the robot through the space to make tea and to use the facilities and so on. And through these interactions with the robot, we recorded a lot of speech, and then we looked at how well speech recognition worked for these individuals talking to the robot. And it turned out that there was a very clear relationship between the accuracy, or the inverse of the word error rate, obtained by speech recognition and the MMSE scores that they obtain. So remember earlier, a score of 30 indicates that someone's cognitively typical, and anything below, say, 27 or 26 indicates that there's some cognitive dysfunction. So obviously, if we want these technologies to be used in the home, we can't have speech-language pathologists and therapists typing out by hand everything that's said. In fact, currently, something like 5 to 10% of all interactions with speech-language pathologists are actually transcribed. We need to do speech recognition at some point. Another benefit of using technologies in the home is that we could do something called reminiscence therapy. So instead of just showing people images of the cookie theft or clinically kind of boring pictures, we can ask individuals to kind of go through their old photo albums, like weddings, for example, and to describe things in those images. So there's lots of evidence that by describing personal histories, people feel better. So there's kind of a reduction in some of the neuropsychological aspects of dementia. But also they talk more, which means we have a lot more information about their speech we could extract clinical information from. Next slide. The overall view, as Elmar intimated earlier, is that there's some kind of a server system that collects conversations from individuals over the phone at home, does analysis partially on the phone, partially on the server. And then these servers have lots of clinical models that can be used to infer stuff about Parkinson's disease, other types of dysarthria, and dementia. In order to get from the lab, from the kind of data we've been dealing with and into the real world, one of the first things we have to do is deal with disparate kinds of tasks. So we have some data of people telling stories. We have other data of people answering questions. We have some data of people doing articulation tasks, like saying Padaka, for example. So typically, it's very difficult to get large amounts of data from individuals with pathology. Sometimes you get 10 to 20 people in each of these kinds of data sets. So we need to be able to combine data sets with very different tasks that people are performing. And we'll talk a little bit about that later today. It's kind of, I mentioned earlier, sometimes it's very hard to find very specific pathologies. There's something called primary progressive aphasia, which is a very rare kind of aphasia. And it's very, very difficult to find individuals, even in very large cities, that suffer from that particular kind of aphasia. But we want to be able to build systems for those individuals too. And we want to build in knowledge of what vascular dementia or Alzheimer's disease sounds like, so we can differentiate through differential diagnosis these different individuals. We have to account for varying ages, levels of education, and languages, so we can't rely on everyone speaking English or speaking English as their first language. And we also want to be able to combine different modalities. So if we have something like the home lab, we have microphones, we have video cameras, we have RFID tags, and so on. We need to be able to unify this kind of information. So one of the first things we did for this workshop was to figure out how much can we do, how accurate can our systems be if we have erroneous speech recognition. So this work was completed before the workshop, but is kind of part of the same stream, and it's going to be presented at InterSpeech in a few weeks. The first thing we did was look at the dementia bank image and the descriptions of the cookie theft picture. And we had a bunch of different parameterizations for our speech recognition system built on Caldi. We did tenfold cross-validation, and then we looked at, across the different folds, was there any relationship between the word error rates of those systems and the overall clinical diagnosis that you could obtain using our traditional methods. And there was some relationship, so there was no impact of various hyperparameters of Caldi, so fiddling with the insertion penalty or the language model weight not seem to have much of an effect on the diagnostic accuracy, but there was some change in how well you could do over time. So if you have very poor speech recognition with about 90% word error rates, you're likely to get about, on the order of 60 to 70% accuracy in diagnosing Alzheimer's disease from those without Alzheimer's disease. Whereas if you have 100% clean transcripts, you can get up to the low 90s. So what we have to do if we're dealing with systems where we don't necessarily have perfect transcripts of speech, if we want to extract a lot of those kinds of features that I mentioned earlier, if we want to extract the counts of adverbs and the proportions of different kinds of syntactic structures. So we looked at how the various 300 lexicosyntactic features that we had extracted change in their importance, whether we use gold transcripts or whether we use transcripts from our best speech recognition system. So in this graph, these bubbles, the location of these bubbles basically represent the p-value in separating Alzheimer's disease individuals with control individuals according to heteroscedastic t-test. On the x-axis is the gold transcripts, on the y-axis is our best WER transcripts. And the size and the color of these bubbles basically refer to the correlation between the values across these transcripts. So this is the linear scale. Here we have the log scale. Interestingly, so down here at the lower left-hand corner, we have some features that are useful in both. So the average word length is always useful whether you use transcripts transcribed by hand or those obtained by a speech recognition system. Up here in the upper right-hand corner, you have features that are really useful in neither. So looking for the word daughter, for example, is not really useful in either situation. But we'll find in this analysis that some features that are useful in the that are not useful in the gold transcripts, like the age of acquisition of verbs, for example, ends up to be a very important feature if you're dealing with noisy data. So if you have transcripts obtained by humans, you use some features, and if you have transcripts obtained by machine, other features kind of pick up the slack for you. So now we're going to start about the meat of the morning. So we have basically two big sections, linguistic analysis and acoustic analysis. So the linguistic analysis will mostly focus on Alzheimer's disease, and these are the three main questions we wanted to pose. The first one was basically whether we can design better task-specific features for people with cognitive disorders. Next, we go on to how can we improve robustness of features across the different domains and tasks that we have, so the fluency task, the conversation task, and the picture description task. And how can we make use of these very disparate data sets to improve runtime performance in general? So first, just talking about the task-specific features. I want to come back to the idea that I mentioned earlier. So our earlier analysis showed that of these 300 lexicosyntactic features that we can extract, if we do a factor analysis, they project into different dimensions. So we have a syntactic dimension and a semantic dimension that more or less refer to verby things and nouny things respectively. And they also have different clinical ramifications. So people with a syntactic deficit might have some degeneration further to the back of the left temporal lobe. People with word finding difficulty might have something in Broca's area that is up. So we want to look at if we can look at these two dimensions independently. So starting off with the nouny semantic topic dimension, we think about other people's work in eye tracking. So there's a lot of cool stuff out there about looking at people's eyes as they're looking at images. There's obviously differences in voluntary movements. People with Alzheimer's disease, their eyes track over an image differently than people without Alzheimer's disease. There's also microscopic saccades, so involuntary movements of the eyes can also be very indicative of Alzheimer's disease. To do this accurately, you need kind of high-tech cameras. You can do reasonably well with like the camera on a tablet, but generally we don't have access to video data for people describing pictures like the dementia bank cookie theft picture that we'll talk about soon. But what we do have is we have the textual descriptions. We know when the person talks about the boy, the mother, the sink, and the girl. And we also have the time at which they talk about these various topics. And we also have kind of the geometric position of these topics over the image. So we can do all kinds of cool stuff with that, which Hamid Reza will talk about first.